The universe is flying apart, and we have no idea why. All the stars, planets, and galaxies we can see account for less than 5% of everything. The rest is a profound cosmic mystery known as dark energy, an invisible force accelerating the expansion of the cosmos. This is not a small mistake in our math. It is a fundamental crack in our understanding of physics itself. By the end of this journey, you will know 30 of the most compelling theories scientists have devised to explain this missing energy. We will explore forces that rewrite gravity, fields that permeate empty space, and ideas that suggest our universe is just one page in a vast cosmic book. Is the answer a simple constant, or is it something that could one day tear reality apart at the seams? What do you believe is truly pushing the cosmos apart? Einstein himself planted the seed for our first theory, though he later tried to uproot it entirely. In an effort to preserve a universe he believed was static and unchanging, he introduced a fudge factor into his equations of gravity, a repulsive force he called the cosmological constant. When Edwin Hubble discovered the cosmos was not static, but in fact expanding, Einstein famously called this constant his greatest blunder and discarded it. The irony is profound because decades later, when astronomers observed the expansion was not slowing down but speeding up, they had to resurrect Einstein's rejected idea. The cosmological constant is now the frontrunner explanation for dark energy. It proposes that empty space itself is not nothing. Instead, the vacuum of space possesses a constant intrinsic energy density, an inherent push that causes the universe to expand at an ever-increasing rate. The elegance of this theory lies in its simplicity. Dark energy is just a feature of space, a fundamental property of the cosmos as unchanging as the laws of physics themselves. But this simple idea comes with an almost unbelievable problem. When physicists calculate how much energy this vacuum should contain based on quantum theory, the number they get is catastrophically large. The predicted value is a number with 120 zeros after it, bigger than any other number in physics. Yet our observations of the universe's expansion require the value to be almost zero, infinitesimally small. This discrepancy of 120 orders of magnitude is the largest and most embarrassing gap between theory and observation in the entire history of science. It means we are either missing something fundamental about the quantum vacuum, or this elegant constant is not the full story. Such a colossal mismatch forces us to ask if the energy of space is truly constant. What if dark energy is not a fixed feature of the cosmos but something that evolves? This question leads us to our second theory, a concept known as quintessence. Imagine a new fifth fundamental force, a dynamic field that stretches across the entire universe. Unlike the rigid cosmological constant, quintessence is alive. It is a form of energy that can change in strength and density over billions of years. In this scenario, dark energy was not always the dominant player. In the fiery chaos of the early universe, its repulsive push might have been utterly insignificant, completely overshadowed by the immense gravity of matter and radiation. This would explain a profound mystery. Why did the accelerated expansion of the universe only begin about 5 billion years ago? If dark energy is a constant, why did it wait so long to take control? A dynamic field like quintessence offers a compelling answer. Its influence could have grown slowly, only recently crossing a threshold where its repulsive force overpowered gravity's pull, initiating the era of accelerated expansion we observe today. Scientists have proposed various models for how this field might behave, such as tracker fields that elegantly follow the energy density of the dominant components of the universe throughout its history. The key difference is that quintessence leaves a traceable signature. A simple constant would push the universe apart at a steady, unchanging rate, but a dynamic field would cause subtle shifts in that expansion rate over cosmic time. Detecting that tiny variation is now one of the great quests in cosmology. Future telescopes, peering deeper into the past than ever before, will hunt for the telltale signs of a force that breathes and changes, potentially rewriting our understanding of the cosmos's final fate. But what if the entire premise is wrong? What if there is no mysterious energy at all, and we are simply misreading the cosmos because our theory of gravity is incomplete? This is the radical proposition behind our third theory, modified Newtonian dynamics, or MOND. It suggests we do not need dark energy nor even dark matter. We just need to rewrite the fundamental rules that have governed physics for centuries. The story of MOND begins not with the expanding universe but within individual galaxies. For decades, astronomers noticed that stars at the outer edges of galaxies were orbiting far too quickly. According to Newton's and Einstein's laws, these distant stars should be flung away into the void. The fact that they are not led to the invention of dark matter, an invisible substance whose gravity holds the galaxies together, MOND offers a different solution. It proposes that on the scale of entire galaxies, where gravity becomes almost unimaginably weak, our equations of gravity subtly break down. In these extreme conditions, gravity does not fade away as the square of the distance, as Newton decreed. Instead, it maintains a stronger grip, which makes it appear as if there is extra mass holding the galaxy together when there is not. This elegant idea successfully explains the rotation of hundreds of galaxies without invoking a single particle of dark matter. But can it also explain the accelerating universe? Some extended versions of MOND, with names like tensor vector scalar gravity, attempt to do just that. They introduce additional fields alongside gravity that, on the vastest cosmic scales, could produce a repulsive effect mimicking dark energy. In this view, the universe's expansion is not speeding up because of a mysterious force, but because gravity itself behaves differently across the cosmic web. The appeal is powerful. It sweeps away two of the greatest mysteries in science with one bold stroke. Yet the challenge is equally immense. For MOND to be a complete theory, it must consistently explain everything. It must account for the precise patterns we see in the afterglow of the Big Bang, the cosmic microwave background. It must explain the intricate motions of colossal galaxy clusters, which seem to be held together by immense, unseen gravitational anchors. So far, no single modification of gravity has managed to cleanly unite all these observations. We are left with a cosmic tug of war. Is the universe filled with invisible, unknown substances, or are we finally seeing the limits of Einstein's magnificent, but perhaps incomplete, vision of gravity? Perhaps the most elegant solution is to unify the two great cosmic mysteries into one. Imagine a single, exotic substance that wears two masks. In the dense, crowded universe of the past, it acts like dark matter, clumping together under gravity to form the scaffolding for galaxies. Then, as the cosmos expands and thins out, it undergoes a dramatic transformation, revealing its second nature as dark energy, pushing the universe apart. This is the bold promise of our fourth theory, the Chaplygin gas. Named after a Russian physicist who studied the aerodynamics of lifting forces, this model proposes that the cosmos is not filled with two separate, unknown entities, but is instead permeated by one unique fluid. Its behavior is dictated by a peculiar and counterintuitive equation of state. For most substances, like the air in a balloon, pressure and density are directly linked. Squeeze the balloon and the pressure inside increases, but the Chaplygin gas is different. Its pressure is negative, and it actually becomes more effective at pushing things apart as its density decreases. In the early, compact universe, this fluid was dense enough to behave just like cold, dark matter, pulling matter together to form the first structures. But as the universe expanded and the fluid's density dropped, its negative pressure began to dominate, creating the repulsive force we now call dark energy. It is a beautifully economical idea, one single answer for two of the biggest questions in physics. Scientists have explored several variations of this model, from the simple original Chaplygin gas to more complex forms called generalized Chaplygin gases, which allow for different rates of transition between its two phases. This theoretical flexibility, however, has become its greatest challenge. As our telescopes have gathered more precise data, the Chaplygin gas has been squeezed from all sides. Observations of distant supernova, which first revealed the accelerating expansion, provide a very specific timeline for when dark energy took over. The subtle patterns imprinted in the cosmic microwave background, the afterglow of the Big Bang, tell us exactly how matter clumped together in the early universe. For the Chaplygin gas to be correct, its single fluid must perfectly match both of these incredibly detailed historical records. So far, no version of the model has managed to fit all the data as well as the standard picture of separate dark matter and a cosmological constant. The elegant unification it offers seems to come at a cost, creating new tensions with observation that it cannot quite resolve. It remains a brilliant and fascinating hypothesis, a testament to the creativity required to solve the universe's deepest puzzles, even as the evidence increasingly points toward a more complex and perhaps less unified reality. While the cosmological constant is a gentle push and quintessence is a slow breath, our fifth theory proposes something far more violent. Phantom energy is a form of dark energy that does not simply persist, it strengthens. Its defining feature is an equation of state where the pressure is not just negative, but more negative than the most negative value allowed by a simple cosmological constant. This seemingly minor mathematical tweak has a catastrophic physical consequence. The repulsive force of phantom energy would not remain steady. Instead, it would grow infinitely stronger as the universe expands. The very fabric of space would not just stretch, it would begin to pull itself apart with ever-increasing ferocity. This leads to one of the most dramatic endings ever conceived for our cosmos, an event cosmologists call the Big Rip. Imagine a future so distant that the acceleration of the universe has become the only force that matters. The first casualties would be the largest structures held together by gravity. One day, the delicate gravitational dance that binds our local group of galaxies together would be overpowered. The Milky Way and Andromeda, which are on a collision course, would be forever wrenched apart, flung into an ever-widening void. As the force intensifies, smaller structures would succumb. The relentless pull of expanding space would tear our own galaxy to shreds, sending stars hurtling into isolation. Next, the expansion would reach into our solar system. The Sun's gravity would no longer be enough to hold its planets. Earth would be ripped from its orbit, a lonely wanderer in an empty sky. The horror would not stop there. As the phantom force grows without bound, it would eventually overcome the forces that hold matter itself together. The same gravitational pull that keeps you on the ground would be rendered meaningless. Then, the electromagnetic forces that bind atoms into molecules and the very nuclei of atoms together would fail. In the final moments before time itself loses all meaning, every planet, every rock, every living thing, and every single atom in the universe would be violently shredded into its fundamental, disconnected particles. The cosmos would end not in fire or ice, but in absolute, total disintegration. This is a profoundly speculative idea, and for good reason. Phantom energy presents serious theoretical problems that make many physicists deeply skeptical. Its existence would likely violate what are known as the energy conditions in physics, rules that prevent exotic matter from allowing things like time travel or faster than light motion. It could potentially lead to violations of causality, where cause and effect become untethered, creating paradoxes that our current understanding of physics cannot accept. While the Big Rip is a fascinating and terrifying possibility, it remains a fringe hypothesis, a stark reminder of the strange and potentially unstable futures that could lie hidden within the mystery of dark energy. The violence of phantom energy presents a cosmic dead end, but a far more elegant transformation could be written into the laws of physics. Our sixth theory suggests the universe did not simply start accelerating, it underwent a fundamental change of state. This idea is known as vacuum metamorphosis. Picture a pot of water on a stove. For a long time, it is just liquid, but as it cools, it reaches a critical point where its properties shift dramatically, freezing into solid ice. The universe itself may have experienced a similar phase transition. The trigger for this cosmic freezing is tied to the expansion of space itself. As the universe grows, the density of matter and radiation drops. There is a key moment when the mass of a background scalar field, a kind of invisible energy present throughout space, becomes comparable to what is known as the Hubble scale, which is a measure of the universe's expansion rate. When these two scales matched, the vacuum of space could have undergone a sudden and profound shift. Its very properties changed, activating a latent, gravitationally repulsive quality. Before this transition, the vacuum behaved normally, allowing gravity to slow the cosmic expansion. After the transition, the vacuum itself became an engine of acceleration. This would explain why the universe's expansion shifted gears so decisively around 5 billion years ago. It was not a gradual takeover, but a flip of a switch, a cosmic phase change that altered the nature of reality itself. This model makes a very specific prediction. Unlike a cosmological constant which exerts a perfectly steady push, the repulsive force in vacuum metamorphosis would have a subtle but distinct signature in how the expansion rate has changed over time. It predicts a specific deviation from the simplest models, a fingerprint that next-generation telescopes like the Nancy Grace Roman Space Telescope are designed to hunt for. This idea is deeply connected to profound concepts in particle physics, particularly symmetry breaking. The Higgs field, which gives particles their mass, is a famous example of a field that underwent a phase transition in the early universe, changing the fundamental forces. Vacuum metamorphosis proposes that we are witnessing a later, grander version of this same cosmic process, a change not in particles but in the fabric of space. The universe may not be running on a simple, unchanging constant, but could be evolving through a series of distinct chapters, each with its own unique set of physical rules. Our universe might be a projection, a cosmic hologram. This is the startling premise of the holographic principle, a theory that reimagines the very nature of reality and could hold the key to our missing energy. To grasp this, picture a black hole. In the 1970s, physicists discovered that the maximum amount of information or entropy a black hole can contain is not proportional to its volume, but to the surface area of its event horizon. All the data describing every star, planet, or person that fell into that vast three-dimensional volume is somehow encoded on its two-dimensional boundary. The holographic principle boldly suggests this is not just a quirk of black holes, but a fundamental property of our entire cosmos. The three-dimensional world we experience, with all its depth and richness, could be a holographic image projected from a two-dimensional surface at the edge of the universe. How could this possibly explain dark energy? The answer lies in information limits. If our universe is holographic, then there is a strict, finite limit to how much information and energy it can contain, dictated by the size of its boundary. This built-in cosmic data cap provides a natural explanation for why the energy of the vacuum is so incredibly small. It cannot be the colossal number predicted by naive quantum calculations, because the universe simply does not have the information storage capacity to hold that much energy. The value of the cosmological constant is not a random, finely tuned accident. Instead, it emerges naturally from the geometry of our holographic cosmos. The small, repulsive force we measure is a direct consequence of the universe hitting its fundamental information limit. This idea creates a profound and beautiful connection. It links the largest scale we can observe, the accelerating expansion of the cosmos driven by dark energy, to the smallest possible scale, the grainy quantum nature of spacetime. The force pushing galaxies apart is inextricably tied to the finite number of bits that can describe reality itself. We are not just living in a universe, we are living on a cosmic hard drive with a fixed capacity, and the faint pressure of dark energy might be the subtle signature of that disk nearing its limit. The holographic universe is a profound idea, but what if our cosmos is not just a projection, but a single slice of something far larger? String theory, a leading candidate for a theory of everything, suggests the fundamental building blocks of reality are not point-like particles but tiny, vibrating strings. To make the math of this theory work, these strings must vibrate in a reality with more than the 3 spatial dimensions we experience. This leads to a breathtaking possibility known as brain cosmology. In this view, our entire observable universe, with all its galaxies, stars, and planets, is a 3-dimensional membrane, or brain for short, floating within a higher dimensional expanse called the bulk. We are forever trapped on this brain, unable to perceive or access the wider dimensions. All the particles and forces we know, like electromagnetism and the nuclear forces, are like paint stuck to the surface of our brain. They cannot leave, but gravity is different. Gravity, according to Einstein, is the curvature of spacetime itself. In a higher dimensional bulk, gravity would not be confined to our brain. It could seep out, leaking into the extra dimensions like water soaking through a sponge. On the scale of our solar system or a galaxy, this leakage would be negligible. But on the vastest cosmic scales, across billions of light years, the cumulative effect of gravity slowly draining away into the bulk could be profound. From our perspective, locked on the brain, it would look exactly as if gravity is becoming weaker over immense distances. This apparent weakening of gravity's pull on cosmic scales could perfectly mimic the effects of a repulsive dark energy. The expansion of the universe would not be driven by a mysterious force pushing out, but by the familiar force of gravity effectively fading away, allowing the cosmos to fly apart faster than we would expect. One of the most famous models exploring this is the Dvali-Gabadadze-Poroti model, or DGP. It provides a specific mathematical framework for how gravity leaks, predicting a precise crossover scale, a certain distance beyond which gravity's leakage becomes significant. This model naturally produces an accelerating universe without needing to invent a new form of energy. It simply uses the geometry of higher dimensions to rewrite how gravity behaves on the grandest stage. The elegance is undeniable, but the challenges are immense. As our cosmological data has become exquisitely precise, models like DGP have been put under a microscope. The specific way they predict the universe's expansion rate should change over time, often conflicts with the detailed timeline recorded by supernova and the cosmic microwave background. Furthermore, these models can create unexpected and problematic side effects like ghost fields, theoretical instabilities that violate fundamental physical principles. The dream of explaining dark energy through extra dimensions remains a powerful and compelling avenue of research, a testament to our attempts to find a deeper, more geometric reason for the cosmos's behavior, even as the data so far suggests the answer might lie elsewhere. But what if the acceleration we measure is not a force, but an illusion born from cosmic geography? All of modern cosmology rests upon a single, elegant assumption that on the largest scales, the universe is smooth and uniform. This cosmological principle allows us to treat the entire cosmos as a simple, expanding fluid. The back-reaction theory dares to challenge this very foundation. It suggests that the universe's lumpiness, its intricate web of galaxy clusters and vast, empty voids, does not simply average out. Instead, the relentless gravitational tug of war between these dense regions and the empty expanses creates a large-scale back-reaction that tricks us into thinking a new force is at work. Think of it like this: you are trying to measure the average depth of a stormy ocean. If you simply take a single, smooth average, you miss the crucial detail that the powerful waves and deep troughs are constantly moving and interacting, changing the overall behavior of the sea. In our cosmos, the voids are the dominant feature by volume. These are unimaginably vast regions, hundreds of millions of light years across, that are almost completely empty of matter. As the universe evolves, the gravitational pull of matter in the dense filaments and clusters acts to slow down their own local expansion. But the voids, being underdense, have weaker gravity and expand much faster. This difference in expansion rates is not a minor detail. The faster expansion of the voids begins to dominate the overall average volume of the universe. When we take our cosmic measurements, we are effectively measuring this volume average. The relentless growth of these cosmic bubbles of nothing creates a cumulative effect that looks exactly like an accelerating expansion, even if no mysterious dark energy is pushing from within. The debate over this idea is one of the most heated in modern cosmology. Skeptics argue that the mathematical models show the backreaction effect is far too small, a mere correction of perhaps 1%, not nearly enough to account for the full strength of dark energy we observe. Proponents counter that we have not yet perfected the models. They believe that when we fully account for the complex, non-linear gravitational dynamics across the entire cosmic web, the effect could be much larger. The true nature of dark energy may not be found in a new particle or field, but in a fundamental misreading of the average behavior of our deeply structured and profoundly lumpy universe. Gravity might not be a fundamental force at all, but a cosmic mirage. This is the radical proposal of physicist Eric Verland, whose theory of emergent gravity suggests we have been misunderstanding the very nature of reality. Just as the concept of temperature is not a fundamental property but emerges from the collective, chaotic motion of trillions of atoms, Verland argues that gravity itself emerges from something more basic, the information encoded in the structure of spacetime. In this view, what we perceive as the force of gravity is actually a statistical effect, a consequence of the universe's natural tendency to maximize its disorder or entropy as it evolves. When matter is present, it disturbs this information content, and gravity appears as a kind of elastic response, a pushback from the fabric of reality as it reorganizes itself. This single shift in perspective has breathtaking consequences. It naturally accounts for the strange rotational speeds of galaxies without needing any dark matter. According to emergent gravity, the observed extra pull holding galaxies together is not caused by invisible particles, but is an emergent effect, a direct result of the way the invisible quantum information of space itself interacts with visible matter. As you move farther from a galaxy's center, the influence of this information landscape changes, creating an apparent additional gravitational force exactly where we need it. The theory goes even further, suggesting a deep connection between the universe's accelerated expansion and this same informational framework. The relentless push of dark energy could be reinterpreted as a manifestation of the universe's evolving information content on the largest scales, a cosmic expression of its entropy. The appeal is intoxicating. It sweeps away two of physics' greatest ghosts with one elegant, information-based mechanism. Yet the skepticism within the scientific community is equally powerful. Critics point out that while emergent gravity can beautifully describe the behavior of individual galaxies, it has struggled to explain the gravitational lensing observed in colossal collisions of galaxy clusters, where the apparent dark matter seems to separate from the visible matter in a way that is hard to reconcile with Verland's model. The theory makes specific, testable predictions about the relationship between a galaxy's ordinary mass and its observed gravitational field, predictions that are now being put to the test by powerful telescopes. The results so far are a mix of tentative support and challenging contradictions, keeping the idea alive but far from proven. Emergent gravity remains one of the most provocative and ambitious ideas on the table, a theory that asks us to forget everything we think we know about gravity and see it not as a force, but as a cosmic shadow cast by the hidden world of information. This staggering mismatch between prediction and reality is not just a problem, it is a screaming clue. The cosmological constant problem is arguably the most profound embarrassment in all of physics. Quantum field theory tells us that the vacuum of space should be a seething, bubbling cauldron of energy. Every cubic centimeter of empty space, according to our best calculations, should contain virtual particles popping in and out of existence, contributing a colossal background energy. The number this calculation produces is unimaginable. It suggests a vacuum energy density of around 10 to the 120 joules per cubic meter. That is a 1 followed by 120 zeros. Yet, when we look at the actual expansion of the universe, the observed energy density of dark energy is almost nothing. It is around 10 to the negative 9 joules per cubic meter. The prediction is 120 orders of magnitude too large. To put that in perspective, it is the difference between the size of a single proton and the size of the entire observable universe. This is not a small rounding error. It is a fundamental crisis, a sign that something is deeply wrong or deeply missing from our understanding of how the quantum world and gravity fit together. So how do physicists try to resolve this catastrophe? One elegant idea is supersymmetry. This theory proposes that every known particle has a hidden superpartner particle. The beautiful mathematical consequence is that the contributions of these particle pairs to the vacuum energy would be perfectly opposite. The positive energy from ordinary particles would be exactly cancelled out by the negative energy from their superpartners, resulting in a net vacuum energy of 0. The problem is, we have never found any of these superpartner particles. If supersymmetry exists in nature, it must be a broken symmetry, meaning the superpartners are too heavy for our particle colliders to detect. And if it is broken, the perfect cancellation is ruined and the problem returns with a vengeance. Another, more philosophical approach is the anthropic principle. This line of reasoning suggests that the value of the cosmological constant is not determined by a fundamental law, but is instead a random variable that can take on different values in different parts of a vast multiverse. In almost all of these universes, the cosmological constant is far too large. If it were positive and big, the universe would have blown itself apart before any stars or galaxies could form. If it were negative and big, the cosmos would have collapsed back in on itself instantly. We find ourselves in a universe with an absurdly tiny but non-zero constant for one simple reason, because this is the only type of universe that allows for the existence of beings like us who can observe it. The cosmological constant is not fine-tuned for life. Life exists because the constant is, by pure chance, in the narrow window that permits it. For many scientists, this feels like giving up on a fundamental explanation, a retreat into metaphysics. Yet it remains a stark possibility. The cosmological constant problem is the ghost at the feast of modern physics. Any true theory of dark energy cannot simply identify its source. It must also explain this incredible, unnatural silence of empty space. This idea of a finely tuned universe forces us to confront a deeply philosophical possibility. The anthropic principle suggests the value of dark energy is not dictated by a fundamental law, but is instead a random accident. To make sense of this, we must envision a multiverse, a cosmic landscape of unimaginable scope where our entire cosmos is just one bubble in a frothing sea of universes. Each of these separate realms could have its own unique set of physical laws and constants. In most of them, the cosmological constant is a cataclysm. If it were much larger and positive, space would have ripped itself apart in the first moments, preventing any star or planet from ever forming. If it were significantly negative, the universe would have collapsed back into a super-dense state almost instantly. Stable, long-lived universes like our own, capable of fostering complexity and life, would be incredibly rare jewels in a vast desert of cosmic failures. We do not observe a universe fine-tuned for life. We observe a universe that permits life because we are here to see it. Our existence acts as a cosmic selection effect, a filter that guarantees we will only ever find ourselves in one of the few hospitable pockets of reality where the numbers just happen to be right. This line of reasoning is both powerful and profoundly unsettling for many scientists. It feels like a retreat from the traditional goal of physics, which is to find a single, elegant, and necessary set of laws that explain why our universe is the way it is. The anthropic principle instead posits that there is no deeper reason. The value of dark energy is a cosmic lottery ticket, and we simply hold the winning number. This makes it a contentious, almost philosophical escape hatch from the cosmological constant problem. Yet, as our theories like string theory continue to suggest a vast landscape of possible vacuum states, each corresponding to a different universe with different properties, the anthropic argument becomes harder to ignore. It shifts the question from why our constants have the values they do, to why we find ourselves in this particular bubble within an infinite foam of possibilities. The mystery of dark energy might not have a neat, fundamental solution within our universe, because our universe might be just one page in a library of realities, most of which are empty and dark. The speed of light is the ultimate cosmic speed limit, a constant so fundamental it is woven into the fabric of physics itself. But what if this pillar of science is not quite as steady as we believe? Our 13th theory proposes a truly radical idea that the speed of light was not always the same. In the fiery infancy of the cosmos, light may have raced across the universe at a rate far exceeding its current value. This concept, known as the time-varying speed of light, or VSL, dares to rewrite the opening chapters of the universe. One of the greatest puzzles of the Big Bang is the horizon problem. Look at the cosmic microwave background, the ancient afterglow of creation, and you will see a nearly perfect uniform temperature in every direction. This should be impossible. The universe was not old enough for light or heat to have traveled from one distant region to another to even out these temperatures. The standard solution is cosmic inflation, a period of unimaginably rapid expansion that smoothed everything out in a fraction of a second. A varying speed of light offers a different, elegant solution. If light traveled infinitely fast in the very first moments, then every part of the newborn universe could have communicated instantly, creating the uniform temperature we observe today without the need for a separate inflationary epoch. This single change could solve multiple problems at once, and it may also hold the key to dark energy. The expansion rate of the universe is governed by a set of equations where the speed of light, c, is a key parameter. If that parameter was different in the past, it would completely alter the cosmic expansion history. A slowing speed of light could create an effect that, from our modern perspective, looks exactly like an accelerating universe. We would interpret the data as a mysterious repulsive force, when in reality we are just seeing the aftermath of a fundamental constant settling down to its current value. The universe would not be speeding up, the rules of the game would have been different all along. This is without a doubt a fringe idea. It requires a complete overhaul of Einstein's theory of relativity, which is built upon a constant c. Changing this single number would send ripples through all of modern physics, forcing us to reconsider everything from the nature of spacetime to the relationship between energy and mass. For most scientists, the evidence for a constant speed of light is overwhelming, supported by countless experiments across vast cosmic timescales. Yet, the theory persists as a testament to the lengths we must go to solve the universe's deepest mysteries. It challenges our most cherished assumptions, suggesting that the very constants we rely on might be nothing more than cosmic variables, still settling into their final fixed values. Our most fundamental constants might not be written in stone. For over 300 years since the time of Newton, we have assumed that the strength of gravity is a fixed number, an unchanging rule of the cosmos. This constant, known as big G, dictates the force of attraction between any two masses. But what if this bedrock of physics is slowly eroding? The theory of a time-varying gravitational constant proposes that big G is not so big after all, that it has been subtly weakening over the billions of years since the Big Bang. The implications for cosmic expansion are direct and profound. The gravitational pull of all the matter in the universe is what has been slowing its expansion. If the very strength of that pull has been fading over cosmic time, then the brakes on the universe are gradually failing. From our perspective, it would look exactly as if a new, repulsive force is taking over and pushing galaxies apart, when in reality, the old force of attraction is simply losing its grip. This idea finds a natural home in a broader class of theories known as scalar tensor gravity. In these frameworks, gravity is not described by Einstein's theory alone. It is accompanied by a background field, a scalar field that permeates all of space. The strength of gravity, big G, becomes tied to the value of this invisible field. As the universe evolves and this field changes, the fundamental strength of gravity changes with it. This is not a small modification. It is a fundamental rethinking of gravity as a dynamic, evolving interaction, not a static force. So how do we test if the pull of gravity is truly constant? Scientists have devised incredibly precise experiments. One method involves firing lasers at retroreflectors left on the moon by the Apollo astronauts. By timing how long the light takes to travel back to Earth, we can measure the Earth-Moon distance with centimeter-level accuracy. Any change in the gravitational constant would subtly alter the Moon's orbit over time, a drift that these laser-ranging experiments should be able to detect. Another cosmic laboratory comes from binary pulsars, pairs of ultra-dense neutron stars orbiting each other at fantastic speeds. These systems are exquisite gravity probes. As they orbit, they radiate gravitational waves, losing energy and spiraling slowly inward. The rate of this inspiral is exquisitely sensitive to the strength of gravity. By monitoring these cosmic clocks for decades, astronomers can search for any tiny deviation that would signal a changing G. The results of these painstaking investigations have so far yielded a profound silence. The gravitational constant appears to be just that, constant. The most stringent limits tell us that if G is changing at all, it is doing so at a rate of less than 1 part in 100 billion per year. This incredible stability places a tight noose around the neck of theories that rely on a rapidly varying gravitational constant to explain dark energy. A changing G could still play a minor role, a faint background hum influencing the cosmos, but it is unlikely to be the solo performer responsible for the grand acceleration we observe. The universe seems to be holding its most fundamental forces steady, forcing us to look elsewhere for the source of its missing energy. The smooth evolution of quintessence is not the only way a dynamic field could fill the cosmos. Another, far more exotic class of theories suggests the key to dark energy lies not in a field's potential, but in its motion. This is the strange world of K-essence, short for kinetic essence. While quintessence behaves like a ball slowly rolling down a gentle slope, its energy dictated by its position, a K-essence field is defined by its raw kinetic energy, by how fast it is moving. Its behavior is governed by a non-standard, highly nonlinear relationship between its motion and its energy density. This unusual property allows K-essence to act as a kind of cosmic chameleon. In the hot, dense early universe, when particles were zipping around at near light speed, the K-essence field would have been effectively frozen, its kinetic energy suppressed, making it completely irrelevant. It would have been a ghost in the cosmic machinery, utterly invisible to the forces shaping the young cosmos. But as the universe expanded and cooled, a dramatic phase change could have occurred. Think of it like supercooled water, remaining liquid well below its freezing point until a single disturbance triggers an instantaneous crystallization. Similarly, the K-essence field might have undergone a condensation, a sudden transition where it switched on, its kinetic energy surging to dominate the cosmos. This would naturally explain the great cosmic coincidence of why dark energy became the dominant force only about 5 billion years ago. The trigger was not a slow climb, but a sudden snap, a fundamental shift in the field state that launched the universe into its current phase of accelerated expansion. Building such a field without creating theoretical monsters is a delicate task. Physicists must carefully craft these models to avoid instabilities like ghosts, which have negative energy, or gradient instabilities, which can lead to uncontrollable waves that shatter the model's coherence. When constructed properly, however, K-essence leaves a unique fingerprint on the universe. Its presence would subtly alter the rate at which cosmic structures, like galaxy clusters and the vast filaments of the cosmic web, grow over time. The repulsive pressure of this dynamic field would act against gravity's pull, making it slightly harder for matter to clump together. This is a signature that the next generation of astronomical giants like the Vera C. Rubin Observatory is poised to hunt for. By mapping the distribution of billions of galaxies across cosmic history, these instruments could detect the faint but distinct imprint of a field driven not by where it is, but by how fast it is moving, revealing a universe propelled by the energy of its own motion. Faster than light travel is not just forbidden, it is a logical impossibility in our understanding of physics. Yet, the mathematics of quantum fields allows for a bizarre hypothetical entity that does exactly that: a tachyon. This is not a particle you could ever catch or see. By its very definition, a tachyon would always travel faster than light, an idea that immediately conjures paradoxes of time travel and broken causality. But within the strange landscape of theoretical physics, the tachyon is not merely a science fiction trope. Its behavior could hold a clue to the universe's missing energy through a process known as tachyonic condensation. Imagine a field that permeates all of space, but unlike ordinary fields, it has a peculiar property. Its potential energy is like a hill, not a valley. In this unstable configuration, any small disturbance would cause it to instantly roll down, settling into a stable state with lower energy. This transition from an unstable high point to a stable minimum is tachyonic condensation. When this field finally settles, its equation of state, the relationship between its pressure and density, can exhibit the exact negative pressure required to drive cosmic acceleration. It would look and act from our perspective like the dark energy we observe. This concept finds a deep and surprising home in string theory. In that framework, the fundamental objects are not just strings but higher dimensional membranes called d-branes. The decay of these unstable, high-energy d-branes is mathematically described by the condensation of a tachyon field. As the brane decays, the tachyon field rolls to its minimum, and in doing so, it could leave behind a residual energy that permeates the vacuum of space. In this view, our entire universe could be the aftermath of a cosmic decay, and the dark energy we measure is the faint, leftover echo of that primordial instability. The appeal of this idea is its deep connection to fundamental physics, but its challenges are monumental. The most glaring issue is causality. Any entity that permanently travels faster than light shatters our understanding of cause and effect. It could lead to information arriving before it is sent, creating logical paradoxes that physics cannot currently resolve. For this reason, most physicists regard tachyons not as real particles, but as mathematical artifacts, signs of an instability in a theory that needs to be corrected. The tachyonic condensate remains a brilliant but deeply speculative ghost in the machinery of string theory, a reminder that the most elegant mathematical solutions can sometimes lead us into territories that reality itself may have declared off limits. A real-world experiment conducted in a laboratory can illuminate the profound mystery of cosmic vacuum energy. The Casimir effect is a remarkable quantum phenomenon where two perfectly smooth, uncharged metal plates, placed incredibly close together in an absolute vacuum, will spontaneously pull towards each other. They are not attracted by magnetism or gravity, but by the very nature of empty space itself. According to quantum mechanics, the vacuum is not truly empty. It is a seething sea of virtual particles, pairs of particles and antiparticles that flicker into and out of existence far too quickly for us to directly detect. These fleeting fluctuations exert a subtle pressure. When the two plates are brought near, they act like a cosmic cage, restricting the kinds of virtual particles that can pop into being in the narrow gap between them. Outside the plates, a wider spectrum of these fluctuations can occur, creating a greater outward pressure. The result is an imbalance, a net force pushing the plates together from the outside. This is not just a theoretical curiosity. Scientists have measured this tiny but real attractive force, providing stunning confirmation that the vacuum of space possesses a real, measurable energy. This is precisely the same vacuum energy that forms the basis for the cosmological constant explanation of dark energy. The energy measured in the Casimir effect and the energy driving the universe apart are two manifestations of the same fundamental quantum reality. Yet here lies the central paradox. The Casimir force is attractive, pulling the plates together, while dark energy is repulsive, pushing the cosmos apart. How can the same vacuum energy produce two opposite effects? The answer lies in the geometry and the boundaries. In the Casimir setup, the metal plates impose a specific configuration, altering the quantum vacuum in a way that creates a pressure differential, resulting in attraction. On the cosmic scale, however, there are no such boundaries. The vacuum energy of free, unbounded space exerts a uniform negative pressure. In the strange logic of general relativity, a uniform negative pressure does not pull things together. It generates a repulsive gravitational force stretching the very fabric of spacetime. This critical difference reveals why we cannot simply take the quantum vacuum energy we understand from small-scale experiments and scale it up to explain the cosmos. The calculations for the cosmological constant involve summing every possible quantum fluctuation across all of space, a process that, without a complete theory of quantum gravity, leads to that infamous catastrophic number 120 orders of magnitude too large. The Casimir effect gives us a tiny, tangible glimpse of the vacuum's latent power, while simultaneously highlighting the immense chasm in our understanding. A clear signal that the true nature of empty space is far more complex and wondrous than we have yet imagined. Einstein's masterpiece, general relativity, is built upon an elegantly simple relationship. The curvature of spacetime is directly proportional to the matter and energy within it. The heart of this theory is the Ricci scalar, a single number represented by the letter r, which describes the overall curvature at any point. For a century, this has been our unchanging guide to gravity. But what if this relationship is not so simple after all? Theory 18, known as F of R gravity, proposes we rewrite the very definition of curvature itself. Instead of the standard Einstein-Hilbert action, which is linear in R, this theory suggests the true law of gravity involves a more complex general function of R, written mathematically as F of R. This single change is deceptively profound. It is like replacing a simple, straight ruler with a flexible, shaped template. The new terms introduced by this custom function do not require any mysterious dark energy. Instead, the modified equations of gravity naturally produce an extra, repulsive component that drives the cosmic acceleration we observe. The curvature of empty space itself, through this new mathematical lens, becomes the engine of expansion. The challenge, however, is to design the perfect F of R function. It must be subtle enough to leave our local cosmic neighborhood untouched. within our solar system, where we have tested general relativity with exquisite precision through planetary orbits and the timing of pulsars, the theory must reduce almost exactly to Einstein's original form. Any significant deviation would have been spotted long ago. Yet on the vast cosmic scale, the function must be bold enough to generate the precise acceleration history we have recorded. It must also flawlessly reproduce the intricate patterns of hot and cold spots in the cosmic microwave background, the blueprint of the early universe. Crafting a single mathematical rule that satisfies all these masters has proven incredibly difficult. Some promising models, like the Sawicki model, are designed to cleverly hide their effects within the solar system while activating their influence across the cosmic voids. Others create instabilities or predict new, long-range forces that have never been detected. The quest for the perfect F of R is a dramatic balancing act, a search for a hidden key that unlocks cosmic acceleration without breaking the beautiful, proven rules that govern the space around us. Hidden sectors of reality might be operating just beyond our perception. Our 19th theory, unparticle physics, proposes exactly that. Developed by physicist Howard Georgi, this idea suggests a completely hidden sector of the universe, a shadow realm with its own rules that interacts with our familiar world of particles only through the feeblest of whispers. The most bizarre property of this hidden sector is scale invariance. In our world, physics changes with scale. The rules governing a subatomic particle are different from those governing a planet. But in the unparticle sector, the physics looks the same at all scales. There is no natural unit of size or energy. This scale invariance has a profound consequence. This hidden stuff would not manifest as discrete particles like electrons or quarks. You could not count them one by one. Instead, it would behave as a continuous, smooth spectrum of states, a blur of existence with no definite mass. This is why Georgi called them unparticles. They are stuff that does not break down into neat, individual pieces. So how could this ethereal, continuous stuff explain the force pushing the cosmos apart? The answer lies in its gravitational footprint. This unparticle sector, despite its weak coupling to our world, would still exert a gravitational pull. Because it is scale invariant, its influence would not diminish with distance in the same way ordinary matter does. It could act as a new, very long-range force that subtly alters the behavior of gravity on the largest cosmic scales. This modification could provide the persistent, repulsive push we attribute to dark energy, all emanating from a hidden, parallel reality that permeates our own. The challenge, of course, is that unparticle physics is profoundly speculative. No experiment has ever detected a clear signature of this scale-invariant stuff. Researchers have proposed ways to find it, perhaps in the delicate energy distributions of collisions at powerful particle accelerators like the Large Hadron Collider, searching for missing energy that carried away by an invisible unparticle. Others have looked for subtle deviations in the precise orbits of planets or in the gravitational lensing of distant galaxies. So far, the universe has kept its unparticle secrets well hidden. This theory represents a breathtaking leap, suggesting that the answer to our cosmic acceleration may not lie in a new property of our own universe, but in the ghostly gravitational tug of a completely separate one, operating by rules so foreign we struggle to even imagine them. Gravity is the force that holds the cosmos together, yet it remains the only fundamental force without a known quantum particle. For decades, physicists have hypothesized the graviton, a massless messenger that would carry the gravitational force, perfectly aligning with Einstein's general relativity. But what if this assumption is wrong? Our 20th theory dares to ask if the graviton itself has a tiny, almost imperceptible mass. This idea, known as massive gravity, could reshape our understanding of the cosmic expansion. In a universe with massless gravitons, gravity is an infinite-range force, its influence fading with distance but never truly vanishing. If gravitons have even a minuscule mass, however, their reach becomes finite. On the scale of solar systems or galaxies, this change would be utterly unnoticeable. But across the vast, yawning chasms between galaxy clusters, gravity's grip would weaken significantly faster than we expect. From our perspective, this apparent fading of the universal attraction would look exactly like a repulsive force taking over. The accelerating expansion of the universe would not be caused by dark energy pushing, but by gravity itself giving up the fight across cosmic distances. This elegant solution, however, was plagued by a theoretical monster for over 40 years. Early attempts to construct a theory of massive gravity consistently produced a pathological instability known as the Boulware-Desir ghost. This mathematical phantom represented a state of negative kinetic energy, a theoretical absurdity that would allow for cascading instabilities, shattering the self-consistency of the entire model and rendering the theory useless. It seemed that a massive graviton was an idea nature itself had forbidden. Then, in a stunning breakthrough, a new model emerged, the work of de Rham, Gabadadze, and Tolley, known as the DRGT model, ingeniously tamed the ghost. By carefully choosing the mathematical terms that describe the graviton's interactions, they found a way to cancel out the ghostly instability, proving for the first time that a consistent theory of massive gravity was possible. This revival has opened a thrilling new front in theoretical physics. The DRGT model and its descendants are not just mathematical curiosities. They make specific, testable predictions about how gravitational waves should propagate across the universe. A massive graviton would travel at a speed slightly less than the speed of light, a tiny deviation that future observatories like the Laser Interferometer Space Antenna, or LISA, could potentially detect. The hunt is now on for the faintest of signatures, a whisper in the ripples of spacetime that could tell us whether the cosmic glue that binds us has a mass after all, and in doing so, rewrite the final chapter of our universe. String theory paints a picture of reality far grander than a single universe. It suggests the cosmos we inhabit is just one possibility in a staggering cosmic library, a collection of potential realities known as the landscape. This theoretical landscape is not a physical place, but a mathematical map of every possible stable or metastable vacuum state that the equations of string theory allow. The number of these distinct configurations is almost incomprehensibly vast, estimated to be around 10 to the power of 500. That is a 1 followed by 500 zeros, a figure so large it dwarfs the number of atoms in our entire observable universe. Each of these possible vacua represents a different universe with its own unique set of physical laws and fundamental constants. The strength of gravity, the mass of an electron, the very number of spatial dimensions could all be different. Crucially, each of these universes would also have a different value for the cosmological constant, the energy of empty space. In this vast landscape, universes with a cosmological constant of 0, or a large positive value, or a large negative value are all common. Our universe, with its peculiarly small positive cosmological constant, is not special or finely tuned by a deeper law. It is simply one address in an immense cosmic metropolis. This framework provides the ultimate playground for the anthropic principle. In the overwhelming majority of universes in the landscape, the cosmological constant is catastrophically wrong for life. If it were much larger, galaxies and stars would never have formed. If it were negative, the universe would have collapsed long ago. We find ourselves in a universe with a tiny, non-zero value for one simple reason, because it is one of the exceedingly rare environments where the conditions are just right for complex structures and ultimately observers to emerge. The landscape offers a profound shift in perspective. It does not explain why the laws of physics are the way they are. Instead, it explains why we observe the laws that we do, given the necessary precondition of our own existence. Yet this grand vision comes with a formidable challenge. How do we test it if the landscape contains 10 to the 500 possibilities, and we can only observe one? how can we ever verify that this breathtaking multiverse is real? The sheer size and complexity of the landscape make it incredibly difficult to derive specific, testable predictions that could confirm or refute the idea. Some physicists argue this moves string theory from the realm of science into the domain of philosophy, a beautiful mathematical construct that may be permanently beyond our experimental reach. Others search for faint, indirect clues, perhaps in the precise pattern of the cosmic microwave background or in the detailed properties of the Higgs boson, that might hint at our universe's place within a wider multiverse. The string theory landscape does not solve the dark energy problem so much as it recontextualizes it, transforming a fundamental mystery of physics into a question of cosmic location and sheer, staggering probability. The universe's acceleration might not be a force at all, but a side effect of cosmic forgetfulness. Building on the idea of emergent gravity, Eric Verland proposes that the very expansion of space is driven by a fundamental need to increase disorder. This is entropic gravity, and it reframes dark energy as a thermodynamic imperative. Think of the cosmic horizon, the farthest point from which light has had time to reach us. According to the holographic principle, this boundary acts like a vast screen containing all the information describing the volume of space within it. Now, as the universe expands, new space is created. With every new cubic centimeter of vacuum, the area of this cosmic horizon increases, and with it, the amount of information the universe can hold. This growth in information, or entropy, is not a passive byproduct. Verland suggests it generates an entropic force, just as a polymer chain will spontaneously straighten out to maximize its disorder. The universe pushes its own horizon outward to accommodate this new information. The acceleration we measure is not a mysterious energy pulling from within, but this cosmic push from the boundary, a relentless drive to maximize the cosmos's entropy. This provides a breathtakingly simple rationale for dark energy. It is fundamentally linked to the arrow of time and the unbreakable second law of thermodynamics, which states that the total disorder of an isolated system always increases. The universe is not accelerating because of a new field. It is accelerating because it must. It is the ultimate expression of a system evolving toward its state of maximum possible entropy. The force pushing galaxies apart is the same force that prevents your coffee from spontaneously unmixing with the milk, a cosmic scale consequence of the same fundamental rule. This thermodynamic engine elegantly sidesteps the need for a cosmological constant, but it remains a profound and controversial leap. Can the relentless drive toward disorder truly be the engine of cosmic destiny? The answer lies in the subtle geometry of information at the very edge of reality. The universe may not have a single, definitive beginning. Instead of a solitary Big Bang, our cosmos could be caught in an endless, rhythmic dance of creation and dissolution. This is the cyclic model, a vision championed by physicists Paul Steinhardt and Neil Turok, where the entire history of the universe repeats in vast cycles stretching across trillions of years. In this grand narrative, the accelerated expansion we observe is not a one-way ticket to a cold, dark future. It is an essential act in a cosmic play that has been running for eternity. Each cycle begins with a universe that is already expanding, filled with a smooth, sparse distribution of matter and radiation. This is the stage set by the previous cycle's dark energy. Here, a dark energy-like field drives a tremendous period of accelerated expansion, much like what we see today. But its role is not to tear the universe apart forever. Its purpose is to cleanse the cosmos. This relentless stretching dilutes the universe to an almost perfect vacuum, wiping the slate clean of all previous structures, galaxies, and even black holes. It smooths and flattens everything, preparing a pristine, empty stage. Only then does the cycle turn. The dark energy field decays, transferring its energy to create a hot bath of new particles and radiation in an event that looks, for all intents and purposes, like a new Big Bang. This is not a bounce from a singularity, but a graceful transition from one epoch to the next, a rebirth from a near vacuum. This model elegantly sidesteps the need for a mysterious initial singularity, that infinitely dense point where all our known laws of physics break down. The universe has always been here, eternally recycling itself. This creates a completely different story for dark energy. It is not a mysterious anomaly destined to lead the cosmos to a cold, lonely end. It is a central, necessary character in an eternal story, the cosmic janitor that cleans the universe in preparation for its next great performance. This cyclic vision makes predictions that starkly contrast with the standard inflationary Big Bang model. For instance, it predicts a specific, faint background of gravitational waves from the transition between cycles that would be far weaker than the signal expected from inflation. Future observatories could one day detect this whisper from the previous universe, offering us a glimpse into the cycle that came before our own. The cyclic model reframes our entire cosmic existence, suggesting that the force pushing our galaxies apart is not an omen of finality, but the herald of a new beginning. The very substance of our reality could be sitting on a fragile foundation. The Higgs field, the invisible energy ocean that gives particles their mass, might not be in its true, lowest energy state. Instead, we could be living in a cosmic bubble of false vacuum, a temporary valley of stability surrounded by a far deeper chasm. Our entire universe, with all its galaxies, stars, and laws of physics, would be an accident, a happy but precarious configuration that is not ultimately stable. This is the haunting premise of vacuum instability. The mathematics of the Higgs mechanism, confirmed by the Large Hadron Collider, suggests this could be true. Our vacuum is likely metastable, meaning it is stable for now, but not forever. It is like a ball resting in a small dip on the side of a vast, steep hill. For billions of years it stays put, but given enough time, a quantum fluctuation, a random tunnel through the energy barrier, could nudge that ball over the edge. This event would not be a slow process, it would be a spontaneous and instantaneous trigger. At a random point in space, a bubble of true vacuum would nucleate. This would not be a bubble of air, but a bubble of a completely new reality with fundamentally different laws of physics. The boundary of this bubble would expand in all directions at the speed of light. There would be no warning. One moment, the universe is as it is. The next, an invisible wall of annihilation sweeps through the cosmos, rewriting the rules of existence as it passes. Every atom, every force, every structure would be instantly and irrevocably transformed into something unrecognizable. Life, consciousness, and memory would simply cease, not in a fiery explosion, but in a silent, fundamental redefinition of what matter is. This connects directly to the mystery of dark energy because the energy density of our current vacuum state is what we call the cosmological constant. The small, repulsive force we measure is a property of this specific, perhaps temporary, vacuum configuration. If our vacuum is indeed metastable, then the dark energy we observe is just the current setting on a cosmic dial that is not yet turned to its final, and for us, catastrophic position. It suggests that the force accelerating the universe is not a permanent feature of reality, but a symptom of our universe's temporary and ultimately unstable address in the landscape of all possible realities. The end would not come from the cold decay of stars or the relentless pull of phantom energy, but from a sudden, silent quantum correction, erasing our cosmic chapter in an instant. Gravity could be slowly draining away from our universe. This is the startling implication of gravitational leakage, a specific mechanism within brain cosmology that reframes the cosmic acceleration. Think of our three-dimensional universe as the surface of a vast cosmic waterbed. When you place a heavy object on a waterbed, it creates a deep depression on the surface, which we feel as the local pull of gravity. But some of the object's weight is also supported by the water and the mattress's deeper bulk. In this analogy, the heavy object is a galaxy or a cluster of galaxies, and the waterbed surface is our brain. The gravity generated by this mass does not just curve the surface of our brain, it also sinks into the higher dimensional bulk. From our perspective, trapped on the brain, this means some of the gravitational force simply vanishes, leaking into dimensions we cannot perceive. On the scale of our solar system or within a galaxy, this leakage is minuscule, almost undetectable. But across the immense voids between galaxy clusters, the cumulative effect becomes profound. Over billions of light years, the relentless seepage of gravity makes the cosmic glue holding everything together appear significantly weaker than it should be. The expansion of the universe is not being actively pushed by a repulsive dark energy. It simply appears to be accelerating because the primary force working to slow it down, gravity, is not as strong as we calculated. The brakes on the cosmos are failing because the brake fluid is slowly leaking out into a hidden reservoir. This elegant idea, however, makes a very specific prediction that we can test. It requires extra dimensions large enough to accommodate this leakage. The size and number of these dimensions dictate how quickly gravity can fade. For decades, physicists have searched for signs of these extra dimensions in the most powerful particle colliders. If they exist, the tremendous energies of particle collisions could potentially blast debris out of our brain and into the bulk, revealing themselves as missing energy in our detectors. So far, the Large Hadron Collider has found no such evidence, placing stringent limits on how large these dimensions can be. They must be smaller than 1,000th of the width of a human hair. Furthermore, the precise observations of gravitational waves from colliding black holes and neutron stars provide another crucial test. These ripples in spacetime travel at the speed of light, and a graviton with any significant mass, a possible consequence of leaking into extra dimensions, would cause these waves to disperse with different frequencies arriving at different times. Our current measurements show no such dispersion, confirming that gravitational waves move at the speed of light with incredible precision. This evidence tightly constrains the possible models of gravitational leakage, suggesting that if extra dimensions are the answer to dark energy, they are incredibly small, or their effects are far more subtle than we had hoped. These cosmic voids are the true titans of our universe, not by their density, but by their sheer, staggering volume. They are the great cosmic deserts, regions hundreds of millions of light years across where the density of galaxies is a tiny fraction of the cosmic average. They are not perfectly empty, but they are the closest thing to nothing that our universe contains. As the cosmos expands, gravity plays a cruel game of favorites. The dense clusters and filaments of matter where galaxies swarm together have a powerful gravitational pull that fights back against the universe's expansion, slowing it down in their local neighborhoods. But the voids, being so underdense, have almost no such resistance. Their gravity is too weak to hold them back, so they expand much faster than the universe's average rate. Imagine a rising loaf of raisin bread where some of the dough is far less dense. Those airy pockets would swell and balloon outward much more rapidly than the dough packed with raisins. This is the fate of our cosmic voids. Over billions of years, they have been growing at an accelerated pace, and they now dominate the total volume of the observable universe. The back-reaction hypothesis asks a profound question. What is the net gravitational effect of this lopsided cosmic battlefield? The dense clusters pull matter inward with their immense gravity and attractive force. But the faster expanding voids exert a kind of gravitational repulsion. In the equations of general relativity, a region that is expanding faster than average effectively creates a repulsive gravitational push on its surroundings. As the voids become ever larger and more dominant, their collective repulsive effect could theoretically outweigh the attractive pull of the clusters and filaments. From our limited vantage point, measuring the average expansion of this deeply flawed cosmic fluid, the result would look exactly like a smooth, mysterious dark energy pushing everything apart. The true driver of acceleration would not be a new force, but a simple, brutal case of cosmic geography, where the emptiness is winning. Scientists are now using some of the most powerful supercomputers in the world to run colossal n-body simulations, modeling the gravitational dance of trillions of particles to see if this back reaction can truly add up. The initial results are tantalizing but contentious. Some simulations suggest the effect is real but far too small, perhaps accounting for only a few % of the observed acceleration. Others, using different methods or accounting for more complex physics, argue the effect could be significantly larger. The challenge is to simulate the entire cosmic web with enough precision to capture the subtle, cumulative gravitational influence of every single void across cosmic history. The question remains open, a testament to the possibility that we are not being pushed by an unknown energy, but are instead witnessing the final, overwhelming victory of nothing over something. The holographic principle offers more than a philosophical picture. It gives us a specific mathematical formula for dark energy. This is the theory of holographic dark energy, a model where the cosmos acknowledges its own fundamental limits. The core idea is beautifully simple. The maximum amount of information, and therefore the maximum energy density that can be contained within any region of space, is not determined by its volume but by the area of its boundary. This is the holographic bound. Apply this to dark energy, and it suggests the energy density of the vacuum in any cosmic volume should be proportional to the inverse square of that volume's characteristic length scale. In plain terms, the larger the cosmic box you consider, the less dense the dark energy within it becomes, precisely because the information capacity of its surface area is now setting the rules. But which length scale defines our cosmic box? This is where the theory branches into different versions, each with profound implications. One compelling candidate is the future event horizon, the farthest distance from which light will ever be able to reach us as the universe continues to expand forever. Think of this horizon as the ultimate boundary of our observable future. If the dark energy density is tied to the inverse square of this horizon's radius, the math produces a value incredibly close to what we actually observe. The numbers align almost perfectly, as if the universe is obeying its own holographic data cap. Another version uses the Hubble radius, the distance beyond which galaxies recede from us faster than light due to the expansion of space itself. This model also derives a sensible dark energy density from holographic principles. The great success of these ideas is their naturalness. They do not require a bizarre, random cancellation of 120 orders of magnitude. The small, non-zero value of dark energy emerges directly from the geometry of our observable universe and the fundamental limit on how much information it can ultimately hold. The energy pushing the galaxies apart is not a mysterious substance, but a direct consequence of the universe hitting its maximum data storage capacity. However, this elegant solution faces a critical test. Can it accurately describe the universe's transition from its past, when matter was dominant and gravity was slowing the expansion, to its present dark energy-dominated era? The holographic model must reproduce the precise moment around 5 billion years ago when the expansion began to accelerate. Some versions of the theory struggle with this crossover. They might predict a transition that happens too early or too late, or they might not quite match the subtle way the expansion rate has changed over time, as recorded by supernova and the cosmic microwave background. The challenge is to find the exact holographic length scale that not only gives the right energy density today, but also writes the correct history for the entire cosmos. This makes holographic dark energy a powerful and testable idea. It connects the largest force in the universe to the most fundamental limit of information, suggesting that the ultimate nature of reality might be written not in energy or matter, but in bits. A universe with a split personality is hiding in plain sight. The symmetron field is a hypothetical cosmic actor that changes its behavior based on its surroundings, a master of disguise that ensures we never notice its presence here on Earth. This is not a uniform field like the cosmological constant. It is a specific type of screened scalar field, a chameleon force that remains dormant where matter is dense but awakens in the great cosmic deserts. Its power comes from a symmetry, a perfect balance that is maintained in high-density regions like our solar system. Here, surrounded by the mass of the Sun and planets, the symmetron field's value is zero. Its symmetry is unbroken and it exerts no force whatsoever. This is why all our local tests of gravity, from the orbit of the Moon to the flight paths of our spacecraft, perfectly match the predictions of Einstein's general relativity. The symmetron is there, but it is perfectly hidden, screened by the matter around us. Yet venture out into the cosmic voids, those unimaginably vast and nearly empty regions between the galaxy clusters, and the situation transforms completely. In these low-density environments, the gravitational pull is too weak to keep the symmetron in check. The symmetry of the field is spontaneously broken. It acquires a non-zero value, suddenly activating and producing a new, repulsive fifth force. This force, emerging only in the emptiest places in the universe, could be the engine of cosmic acceleration. It would not push from within galaxies or clusters, but from the immense, growing voids themselves, giving the entire cosmos an extra outward shove. This elegant idea provides a beautiful solution to a major problem in modified gravity. How do you change gravity on cosmic scales without breaking it here at home? The symmetron field answers by being a cosmic introvert, silent in crowds but powerful in solitude. The hunt for this elusive field is now underway in two extreme arenas. In deep space, astronomers search for subtle distortions in the shapes of galaxies at the edges of giant voids, looking for the telltale sign of an extra force at work. Meanwhile, in highly sensitive laboratory experiments here on Earth, physicists are using incredibly precise atomic instruments to try and measure the infinitesimal force a symmetron would exert over tiny, ultra-high vacuum chambers, where the local density is low enough for the field to potentially reveal a whisper of its presence. We may be on the verge of discovering that the force shaping the entire cosmos has been hiding in the emptiness all along, waiting for us to learn how to look. The ultimate fate of the cosmos hinges entirely on the true identity of dark energy. If it is a simple cosmological constant, the universe is on a one-way trip to a state known as the heat death or big freeze. In this future, the acceleration continues at a steady, unyielding pace. Galaxies will be pulled so far apart that the light from one will never again reach another. Stars will burn through their fuel and die one by one until the last embers in the universe fade to black. Black holes will slowly evaporate over trillions upon trillions of years. The cosmos will become a vast, ever-expanding and profoundly cold emptiness where the temperature uniformly approaches absolute zero. It is an end of isolation, a quiet, dark, and eternal fade. Yet if phantom energy is real, the end will be anything but quiet. The universe would face a violent demolition called the Big Rip. The accelerating force would not just persist, it would grow infinitely stronger, overwhelming every binding force in nature. Long before the final moment, galaxies, solar systems, and even planets would be torn asunder. In the last horrific fraction of a second, the phantom force would rip apart atoms, nucleons, and the very fabric of spacetime itself. This is not a slow cooling, but a total and absolute disintegration of reality. There is, however, a third, more hopeful possibility woven into the cyclic model. Here, dark energy is not an agent of destruction, but a cosmic reset button. Its job is to expand and dilute the universe to a near-perfect vacuum, wiping the slate clean of all structures, preparing the stage for a new Big Bang and a fresh cycle of creation. In this view, our accelerating expansion is not a final chapter, but merely the closing act of one performance in an eternal cosmic play, soon to be followed by a new beginning. The quest to understand dark energy is therefore far more than an academic puzzle. It is a journey to answer the most profound question of all, whether our universe is destined for eternal ice, sudden annihilation, or perpetual rebirth. The fate of the cosmos will not be decided by mathematics alone, but by the silent testimony of light collected from the edge of time. Across the globe and in orbit, a new generation of cosmic detectives is now tuning its instruments, preparing to put every single one of these 30 theories to the ultimate test. The Euclid Space Telescope, for instance, is not simply taking pretty pictures. It is embarking on a painstaking, three-dimensional survey of the sky, designed to create the most precise map of the dark universe ever made. It will stare at billions of galaxies, measuring their shapes and positions with microscopic accuracy. Its primary tool is weak gravitational lensing, a subtle but powerful phenomenon. As light from these distant galaxies travels across the cosmos toward us, it passes through the invisible gravitational fields of dark matter and the warped geometry of space itself. These fields act like a vast, lumpy lens, subtly distorting the shapes of the galaxies, stretching them into faint, coherent arcs. By analyzing this distortion across the entire sky, Euclid can trace the distribution of both dark matter and the influence of dark energy, revealing how the cosmic web has been stretched and pulled over billions of years. Simultaneously, from the high deserts of Chile, the Vera Sea, Rubin Observatory will unleash its legacy survey of space and time, a relentless 10-year movie of the southern sky. Its enormous mirror will scan the heavens night after night, discovering countless supernovae. Each of these exploding stars is a standard candle, a beacon whose known intrinsic brightness allows astronomers to measure its distance with incredible precision. By comparing these distances across cosmic time, scientists can chart the expansion history of the universe in exquisite detail, seeing exactly how the rate of acceleration has changed and whether it matches the steady push of a cosmological constant or the evolving breadth of a quintessence field. Then there is the Dark Energy Spectroscopic Instrument, or DESI. Mounted on a telescope in Arizona, it is not just looking at where galaxies are, but precisely measuring their individual distances. It does this by capturing the light from tens of millions of galaxies and splitting it into a spectrum, a rainbow that reveals how much the universe has stretched since that light began its journey. This allows DESI to map the universe in 3 dimensions on a scale never before attempted. Within this vast cosmic cartography, it hunts for a specific fossil imprint known as Baryon acoustic oscillations. In the early universe, pressure waves, like sound waves, rippled through the hot plasma, creating a preferred spacing between galaxies. This spacing acts as a cosmic ruler, a standard rod of known length etched into the fabric of the cosmos. By measuring how the apparent length of this ruler has changed as the universe expanded, astronomers can measure the expansion history with yet another independent method, cross-checking the results from supernova and lensing. These missions are not working in isolation. They are a coordinated assault on the same mystery, each method probing a different facet of dark energy's influence. The data they are now collecting will create a verdict that no amount of theoretical elegance can override. It will tell us if the cosmological constant is truly constant or if a dynamic field is at play. It will reveal whether our gravity needs modification or if the backreaction of cosmic voids is stronger than we thought. The road ahead is paved not with speculation but with light. The universe has held its secret for 14 billion years, but its silence is about to be broken by the collective gaze of a curious species, determined to read its final chapter. We have traveled through 30 of the strangest and most brilliant corners of modern thought, from Einstein's resurrected constant to the ghostly pull of emergent gravity. This is more than a single mystery. It is a fundamental confrontation with everything we think we know. The very laws of physics, tested and trusted for a century, are now being questioned by the silent, accelerating drift of the galaxies. The solution, when it finally arrives, will not just answer one question. It will rewrite our understanding of reality itself, reshaping our concepts of space, time, and the vacuum from which everything emerged. This grand search, spanning telescopes, particle colliders, and the pure power of human reason, stands as one of the most profound adventures in the history of science. So we turn the question to you: which of these possibilities captures your imagination the most? Do you believe the answer is a new form of energy, a subtle modification of Einstein's gravity, or something so entirely new it currently lies beyond our imagination? Share your favorite theory in the comments below, subscribe for more journeys to the edge of understanding, and as always, keep looking up. The true weight of this mystery settles in when you realize it cannot be solved alone. Dark energy is not an isolated anomaly in the cosmos. It is one vital thread in a much grander tapestry, woven tightly together with the universe's other profound secrets. Consider dark matter, that invisible gravitational glue holding galaxies together. For decades, we have treated it and dark energy as separate entities, two different unknowns to be catalogued and solved. But what if they are two different faces of the same fundamental phenomenon? Perhaps they are both manifestations of a single, deeper structure in the fabric of spacetime, a structure that reveals itself as attraction in one context and repulsion in another. Unlocking one could instantly unravel the other, giving us the key to both the scaffolding and the engine of the cosmos. This interconnected web stretches all the way back to the very beginning. The initial conditions set by cosmic inflation, that fraction of a second of hyper-expansion that smoothed the infant universe, are inextricably linked to the dark energy we see today. Inflation was driven by a repulsive force acting on a microscopic quantum scale. Dark energy is a repulsive force acting on a cosmic scale. Are they different chapters of the same story? Is dark energy a faint, lingering echo of that primordial inflationary push, or a second act triggered by the universe's expansion reaching a critical point? The answer ties the universe's birth directly to its long-term fate. Ultimately, all these threads converge on the same fundamental challenge: the quest for a theory of quantum gravity. For a century, general relativity has ruled the cosmos while quantum mechanics has governed the subatomic world, and the two have refused to speak the same language. Dark energy is the screaming paradox at their border. It is a quantum phenomenon, the energy of the vacuum, that should be generating a gravitational effect. But when we use general relativity to calculate that effect, we get a number that is catastrophically, embarrassingly wrong. This tells us in no uncertain terms that we are missing the bridge. A true theory of quantum gravity would not just tell us how gravity works for a single particle. It would describe how the quantum vacuum gravitates, finally explaining why empty space pushes the universe apart. It would reframe both dark matter and inflation within a single, coherent framework. Solving the dark energy puzzle is therefore about much more than finding a missing component. It is about discovering the Rosetta Stone that will allow us to read the universe's entire history, from its first quantum tremor to its final, fading breath. We are not chasing 30 separate theories. We are circling a single, profound truth about reality, waiting for the final piece to click into place.